Ever wondered what makes tree interviews both tricky and fun? Lowest common ancestor of a binary search tree is a Pattern Mastery 100 favorite, routinely used by Google, Facebook, and Amazon to test how well you exploit BST properties. More than 30% of candidates overcomplicate it or miss the power of BST traversal. Let's make sure you're not one of them. Let's solve lowest common ancestor of a BST using the basic framework, a stepwise guide that ensures you never miss an optimization or edge case. Now let's break this down. You're given the root of a binary search tree, BST, and two nodes, P and Q. Your task? Find their lowest common ancestor, LCA, the deepest node in the tree that has both P and Q as descendants. Input, root node of a BST, and two node references P and Q. Output, the node representing their lowest common ancestor. Here is a real-world example. Imagine managing folder permissions in a company's shared drive. To find the closest shared folder for two users' files, you need the LCA. Or, in a genealogy tree, to find the nearest shared ancestor between two people. Let's assess it. What's tricky? With a normal binary tree, you'd need to search both subtrees recursively. But in a BST, every node's left children are smaller, and right children are larger, so you can leverage value comparisons to avoid unnecessary work. Now let's think step by step. Start at the root. If both P and Q are less than root, both nodes are in the left subtree, go left. If both P and Q are greater than root, both nodes are in the right subtree, go right. Otherwise, root is between P and Q, or equals one of them, that's the split point, and the LCA. Let's clarify. You don't need to visit every node. BST ordering lets you home in on the ancestor in OH time, where H is tree height. Edge cases. One node is ancestor of the other. Nodes are on different sides of root. Root is LCA. Here is the structure. Start at root. While root is not null, if both P and Q are less than root, go left. If both are greater than root, go right. Else, root is the LCA, return it. If root becomes null, shouldn't happen for valid input, return null. Now let's implement the iterative BST property approach, walking down the tree until we reach the split point between the two nodes. We start by defining our solution class, just a container for the method we're about to write. This function finds the lowest common ancestor, or LCA, of two nodes P and Q specifically in a binary search tree. Because it's a BST, values guide the path, making it very efficient. Time complexity, OH, where H is the tree height. We create a pointer cur starting at the root. We'll use this to walk down the tree following BST rules. We keep looping as long as our pointer hasn't wandered off the tree. Each loop narrows down the search for the LCA. Here's the key BST insight. If both P and Q have values smaller than cur, that means both nodes are somewhere in the left subtree. So we simply move left. We shift our pointer to the left child and continue our search. Now we check the opposite direction. If both values are greater than cur, that means their LCA must live in the right subtree. So we move right. We slide the cur pointer down one level to the right. If neither of the previous conditions is true, it means something important. P and Q are now on different sides of the current node, or one of them is the current node. In all those cases, we've reached the lowest common ancestor. We return the node sitting in cur, because it's the one closest to both P and Q without going past them. That's our LCA. And that's how this algorithm works. It first starts from the root, then uses BST rules to steer left or right until the moment where the two nodes split paths. Efficient, simple, and elegant. Let's test our iterative BST-based solution using this input. This array represents a binary search tree where 6 is the root. Left subtree of 6, 2 with its children 0 and 4, and 4 has children 3 and 5. Right subtree of 6, 8 with children 7 and 9. We're asked to find the lowest common ancestor, LCA, of the nodes with values 2 and 8. In a BST, all values in the left subtree are smaller than the root, and all values in the right subtree are greater. We can use this property directly. Start at root 6. We check P equals 2 and Q equals 8. One value, 2, is less than 6, and the other value, 8, is greater than 6. As soon as we see that P and Q lie on different sides of 6, we know 6 is the split point, and that makes 6 the lowest common ancestor. We don't even need to go deeper. And that's exactly what our function returns, 6, matching the expected result. So, our implementation is correct. The iterative BST property solution quickly finds the LCA by just walking down the tree and stopping at the split point. Simple, efficient, and spot on. Now let's implement the recursive BST property method, narrowing the search by moving left or right until the lowest common ancestor is found. We begin by defining our solution class, which simply groups our method nicely. This function finds the lowest common ancestor of nodes P and Q in a BST. This approach works by recording the path from the root to each node, and then finding the last shared node. Time complexity, OH, where h is the height of the tree. We define a helper function called findPath. Its job is to walk down the BST and record each step until it reaches the target node. We create an empty list called path. This will store every node we visit on the journey to our target. As long as we haven't run out of tree, we keep exploring downward. We add the current node to the path, sort of like dropping breadcrumbs along our route. If the target value is smaller than the current node's value, we know, thanks to the BST rules, that the target must be in the left subtree. So we move left and continue the search. If the target value is larger than the current node's value, then it must live somewhere in the right subtree. So we move right. If neither condition applies, we've arrived at the target. We break out of the loop. The completed path, from root all the way to the target, is returned. We compute the full path from the root to node P, and we do the same for node Q. Now we have two lists representing their roots through the BST. We initialize LAK, which will eventually hold the lowest common ancestor. We loop through both paths together, comparing nodes at the same positions. This works because paths start at the root and diverge only when P and Q split. If the nodes match at this position, that means both P and Q share this ancestor. We update LCA. We store this node as the newest shared ancestor seen so far. As soon as the paths disagree, the shared ancestry stops, so we break. We return the last node they had in common, which is exactly the lowest common ancestor. And that's how this algorithm works. It first records the paths from the root to each target node, then compares the paths to find the deepest shared node. Efficient, simple, and elegant. Now let's check. This tree represents a simple BST. 2 is the root. 1 is the left child of 2. We want the lowest common ancestor, LCA, of the nodes with values 2 and 1. With the find paths and compare approach, we find the path from the root to P, find the path from the root to Q, compare the two paths from the start and track the last common node. Let's write the paths. Path to P equals 2. Start at root 2. We're already at the target path is, path underscore P equals 2. Path to Q equals 1. Start at root 2. Since 1 less than 2, go left to 1. Reach target path is, path underscore Q equals 2, 1. Now compare the paths element by element. First element, 2, from path underscore P, and 2 from path underscore Q, match. Path underscore P ends here, while path underscore Q continues to 1. The last common node between the two paths is 2. That means the lowest common ancestor of 2 and 1 is node 2. And that's exactly what the program returns. So, our implementation is correct. The path-based method correctly identifies the root 2 as the lowest common ancestor in this small BST. If BST questions ever felt abstract, this one makes them click. The lowest common ancestor of a BST shows how a tiny ordering rule can guide you straight to the answer without searching everything. Let's do a recap. We're given a BST plus 2 nodes, P and Q. The goal is to return the lowest common ancestor, the deepest node that has both P and Q in its subtree. In plain terms, the closest shared parent in a value-ordered tree. The key advantage is the BST property. Left subtree values are smaller, right subtree values are larger. Instead of exploring both sides like a general tree, we compare P and Q against the current node's value to decide which single direction to go, or to stop at the exact split point. Start at root and loop, or recurse, with 3 simple checks. If P and Q are both smaller than the current node, go left. If both are larger, go right. Otherwise, you've hit the split, or matched one of the nodes, and that current node is the LCA. We followed that plan directly, using straightforward comparisons at each step. No extra data structures, no exhaustive search, just clean movement left or right until the split point appears. We ran it on LeetCode and verified the logic. When P and Q sit on opposite sides, the root at the split is returned. When one is an ancestor of the other, that ancestor is the answer. Edge cases like the root being one of the targets and tiny trees behaved exactly as expected, and everything executed without errors. The takeaway, in a BST, order is a compass. Let value comparisons guide your traversal, and the LCA reveals itself in OH time. No backtracking, no fuss.